Okay, so we're in chapter 12, and we're going to go back to our scenario where we're in section 12.2, and we're looking at the chi-squared test of independence or association. And we were talking about the scenario with Chapek 9 and how to differentiate using a specific question to determine whether or not a visitor is a robot. And so we are going to open up our Chapek CSV file. So we just downloaded it, and here we go, downloads. I'm going to choose this one. All right, there it is. And so we'll notice that we have the unique identifier, we'll have the species and the choices in our data set. Yep, we got that. And in total, there are 180 entries in this data set, and there's one for each person. And our data set looks to be counting robots and humans as people. And specifically, there are actually 93 humans and 87 robots. Overwhelmingly, the preferred choice is the data file. So you can check this yourself by asking JASP for a contingency table. And the contingency table is defined as a statistical tool that displays the frequency distribution of variables to analyze the relationship between categorical variables. All right, so again, we're gonna make a contingency table, which is a statistical tool that will display our frequency distribution of our variables in our scenario to analyze the relationship between the categorical, which is nominal, variables. All right, so here we go. We opened up Chapek 9 data file in JASP, and then we're going to follow these steps. So we're going to select frequencies. Okay, we're going to go to classical, and we're going to select contingency tables. We're going to move choice to the rows box. Species to the columns box. Okay. And we're going to check our output with figure 12.7, which is on page 12. So let's look. So we're seeing our output, and we have oh, that's actually pretty interesting. So under human, we have 65, 13, 15, 93, 44, 30, 13, 87. Under robot, we have our totals 109, 43, 28, and 180. Underneath that, we get our chi-squared tests, and we have a value of 10.72. Degrees of freedom is 2, and the p-value is 0.005. N equals 180. Okay, looks good. Let's go back to page 11. So again, here's our contingency table, and this particular table is shown as a 3x2 contingency table. So we can see, yep, we can see that. To read a contingency table, we've done this before, but You'll recall that you're going to identify the variables from the row and column headings and then examine the cell frequencies to see how the observations are distributed across categories. So in our table, the rows represent the 3 levels of choice of the choice variable. Our columns represent 2 levels of the species variable. Okay. We look at the intersection of a row and a column, and then we determine the count for that particular combination of values. Yeah. So again, we just went through this. We have 65 humans who chose data, 13 humans who chose flower, and 15 who chose puppy. Okay. And there were 93 humans and 87 robots in our sample. In the last column, we have the row tools. Sorry, let me blow that up. We have our row totals, and there were, I see 109 participants who chose data, 43 who chose flower, and 28 who chose puppy. And again, it's for a total of 180. So that looks good. So from our figure, it is quite clear that the vast majority of the humans chose the data file. Okay. Whereas the robots tended to be a lot more even in their preferences. So let's see. Yep, I see that. So leaving aside the question of why the humans might be more likely to choose the data file, our first order of business would be to determine if the discrepancy between human choices and robot choices in the data set is statistically significant. So now we're going to construct our hypothesis test. Okay, so again, how do we analyze our data? We're now in section 12.2.1, page 12. So specifically, since this research hypothesis is that humans and robots answer the question in different ways, how can we then construct a test of the null hypothesis that humans and robots answer the question the same way? So just like before, by establishing some notation to describe the data, we can describe it this way. Okay, so we have our chart on page 12. So there's our output. We have our column robot, our column human, and our total. And so we have our observations, and then we have our notations. So let's say that O subscript I subscript J is a count of observed frequency of the number of respondents that are of the species J, whether it's robots or human, who gave answer I, which was puppy, flower, or data, when asked to make a choice. The grand total is written as N as usual. Finally, I've used R subscript I to denote the row totals. And R1 is the total number of people who chose flower. Okay. And then C subscript J is denoting the column totals, where C subscript 1 is the number of robots. Okay. So now we're going to think about what our null hypothesis actually says. So if robots and humans are responding in the same way to the question, okay, it means that the probability that a robot says puppy is the same as the probability that a human says puppy, and so on for the other two possibilities. So if Pij denotes probability of a member of species J gives response I, then this would be our null hypothesis, top of page 13. So it's a big one. So our null hypothesis would be that all of the following are true. So let's see. So P11 equals P12, P21 equals P22, and P31 equals P32. So first it says that same probability of saying puppy. Then it says same probability of saying flower. And then it says same probability of saying data, but it can actually appear, right, with mathematical notation a little bit, a little bit vague. So actually, since the null hypothesis is just claiming that the true choice probabilities do not depend on the species of the person making the choice, we can just let P subscript I refer to this probability. So for example, we can say P1 is the true probability of choosing the puppy. Next, in the same way that we did the goodness of fit test, what we need to do is calculate the expected frequencies. So that is for each of the observed counts, right, O, I, J, we need to figure out what the null hypothesis would tell us to expect. So let's denote this expected frequency as EIJ. This time it's a little bit trickier. If there are a total of CJ people that belong to species J, and the true probability of anyone, regardless of species, choosing option I is PI, then the expected frequency is this calculation. EIJ equals CJ times PI. So we do have a little minor problem. So unlike the situation we had with the goodness of fit test, the null hypothesis doesn't actually specify a particular value for PI. It's something we have to just estimate from the data. Fortunately, it is pretty easy to do. So if 28 out of 180 people selected flower, then a natural estimate for the probability of choosing flower is just 28 divided by 180. We've done this before, so that would be 0.16. So if we phrase this in terms of mathematics, right, and we come up with an alternate equation, what we're saying is basically that our estimated probability, so P with a little hat, subscript I, so if we estimate that for the probability of choosing option I, we get Ri in the numerator divided by n. So therefore, the expected frequency can be written as the product of the row total and the column total divided by the number of observations. So we see that equation. And then now that we've figured out how to calculate expected frequencies, it looks pretty straightforward to define a test statistic following the same strategy that we used in the goodness of fit test. And in fact, it is the same statistic, but slightly different. This equation, as we can see on page 13, for the contingency table with R rows and C columns, the equation that defines the chi-squared statistic, it's chi-squared equals sum R, sum C, and then our numerator, denominator, same as before. The only difference is that we have to include two summation signs, as we can see, which indicate that we're summing over both rows and columns. So as before, large values of chi-square indicate that the null hypothesis provides a poor description of the data. Whereas small values of chi-squared suggest that it does a good job of accounting for the data. Therefore, just like last time, we're going to reject the null hypothesis if the chi-squared is too large. So this statistic, right, is chi-squared distributed, and all we need to do is figure out how many degrees of freedom are involved, which actually is not hard. So as mentioned before, you can just think of the degrees of freedom as being equal to the number of data points that you're analyzing minus the number of constraints. So the contingency table with rows R and C columns contains the total of R times C observed frequencies, and that's the total number of observations. And what about your constraints? So this is a little bit trickier, but the answer is always the same. So this is going to be R minus 1 multiplied by C minus 1 to get your degrees of freedom. So the explanation for why the degrees of freedom will be a little different depending on the experimental design. So for the sake of argument, we can suppose that we had intended to survey exactly 87 robots and 93 humans, and the column totals were fixed by the experimenter, but left the row totals free to vary. So the row totals are random variables. All right, moving to page 14. So then let's think about the constraints that would apply in that scenario. So since we would deliberately fix the column totals by the act of the experimenter, we have C constraints there. So remember how the null hypothesis had some free parameters, like we had to estimate the PI values. So those also matter here. Every free parameter in the null hypothesis is like an additional constraint. So then we have to figure out how many of those are present. So since the probabilities have to sum to 1, there's only R minus 1 of these, okay? So here's a really long calculation, but what it says is number of observations minus number of constraints. So here we have our equations, which give us our R minus 1 times C minus 1. Alternatively, you could suppose that the only thing that the experimenter fixed was the total sample size, and so that means that we quizzed the first 180 people that we saw, and it turned out that 87 were robots and 93 were human. And then this time around our reasoning, it would be slightly different, but would still lead us to the same answer. So our null hypothesis still has R minus 1 free parameters corresponding to the choice probabilities, but it now also has C minus 1 free parameters, which correspond to the species probability. So because we'd also have to estimate the probability that a randomly sampled person turns out to be a robot. So finally, we would fix the total number of observations, or N, and that one And that's just one more constraint basically. So now we have R times C observations, which is your C minus 1, and then that value plus R minus 1 plus 1 constraints. So what does that give? So we can see that equation listed here. So now let's go ahead and we'll do the chi-square test of independence in the software. So we're on page 14. So now that we know how the test works, we're going to take a look at the software and to remind everybody, we just recently did the goodness of fit test in the last section. Since this test of independence, the chi-square test of independence, conceptually is not any different, we're not going to do any long calculations here. Instead, we're just going to jump into the software and keep going. So for this example, we're going to again use the Chapek 9 data set and construct the contingency table, which we already did. And so when we go back to that, we're going to go under, we have choice and species, go under statistics in this part. So there you go. And now we're going to look at the phi and the Kramer's 5. So let's find that. That's under nominal. So you have to scroll down a little bit. So we have some choices under nominal, right? And we also have some choices under ordinal. So we're selecting phi and Kramer's V. And then we get our values calculated there. All right, so we can compare our output to figure 12.8, so let's go do that. So chi-squared equals 10.72, degrees of freedom is 2, and our p-value is 0.005, and n equals 180. Under nominal, we have our phi coefficient and our Kramer's V, 0.244. So let's double check. We're using, this, and that's correct. And then we can go under our counts, and we can show totals. All right, so again, our chi-square test value comes out to the 10.72, 2 degrees of freedom, and the p equals 0.005. The Kramer's V can be reported as a measure of effect size, and here the V equals 0.244. And let's keep going. Now we're on page 15. So the output gives us enough information to write it up this way. So the Pearson's chi-square revealed a significant association between species and choice. Chi-squared 2 equals 10.72, comma p equals 0.005. Kramer's V equals 0.24. Robots appeared to be more likely to say that they prefer flowers, but the humans were more likely to say they prefer data. And notice that once again, there was a little bit of interpretation provided to help the human reader understand what's going on in this data set. But later on in the discussion section, the author would go on to provide a bit more context. So to illustrate that example, we can see the following, and this is what they would say. So the fact that humans appear to have a stronger preference for raw data samples than robots is somewhat counterintuitive. However, in context, it does make sense. And as the civil authority on Chapek 9, it has an unfortunate tendency to kill and dissect humans when they are identified. So as such, it seems most likely that the human participants did not respond honestly to the question, so as to avoid potentially undesirable consequences. So this should be considered to be a substantial methodological weakness, right? Okay. So this could be classified as a rather extreme example of a reactivity effect. Obviously, in this scenario, the problem is severe enough that the study is more or less worthless as a tool for understanding the different preferences among humans and robots. However, the illustration does show the difference between getting a statistically significant results, right, and how to do the exercise. And our null hypothesis is then going to be rejected in favor of the alternative, right, because p-value is less than 0.05. And finding something of scientific value, right? So the data will tell us nothing of interest about our research hypothesis due to a big methodological flaw. Next, we're going to get into something called the continuity correction. So let's pull that up here. So the continuity correction. So we're on page 16, section 12.3. So let's see. So we're going to digress a little bit, and the author is saying that there's going to be a tiny change in how to make calculations whenever you only have 1 degree of freedom. And this is something called the Yates correction or the continuity correction. So this author pointed out earlier that the chi-square test is based on an approximation, specifically on the assumption that the binomial distribution starts to look like a normal distribution when you have a large n. One problem with this is that it doesn't quite work, especially when you've got only 1 degree of freedom. Like if you're doing a test of independence on a 2x2 contingency table. So the main reason that it doesn't quite work is that the true sampling distribution for the chi-squared statistic is actually a discrete variable, right? Because you're dealing with categorical data. But the chi-squared distribution is continuous, okay? So this can introduce a systematic problem, specifically when n is small and the degrees of freedom equals 1. So the goodness of fit statistic, it tends to be too big, meaning that you actually have a bigger alpha value than you think. So equivalently, the p-values are a bit too small. So in 1934, Yates suggested a simple fix. We can see this equation on page 16. And here in this equation, we're going to redefine the goodness of fit test statistic. Okay, so we can see how they're doing that. And basically, he subtracts 0.5. As far as this author can recall from reading Yates' paper, the correction is basically just a quick hack, and it's not derived from any principled theory. It's just based on an examination of the behavior of the test and observing that the corrected version seems to work better, okay? this author is observing that the corrected version does work better. So you can specify this correction under JASP by going under Statistics and checking the box next to chi-squared continuity correction. You can also see that in figure 12.9. So let's go look. So we see statistics and you can check continuity correction. And this is when you're conducting a 2x2 chi-squared test of independence using the chi-squared continuity correction to request the Yates continuity correction. So the next section we're going to cover is effect size. Now, it is becoming commonplace to ask researchers to report some measure of effect size when they report their data. So let's suppose here that you run your chi-square test, which turns out to be significant. So you will know that there is some association between your variables by doing your independence test, and there will be some deviation from the specified probabilities, right, under the goodness of fit test. So now you want to report a measure of effect size, okay? So you want to be able to discuss, right, how strong is this association or deviation. So there are several different measures that you can choose when reporting and several different tools that you can use to calculate them. We're going to focus here on the most commonly reported measures of effect size, which are the phi coefficient and the somewhat superior version known as the Kramer's V. So mathematically, they're simple. To calculate the phi statistic, you divide your chi-squared value by the sample size, and then you take the square root. The idea here is that the phi statistic is supposed to range between 0, which means that there's no association at all, and 1, which is perfect association. But it doesn't always do that when your contingency table is bigger than a 2x2, which is pretty much a big pain. So when you have a bigger table, it is possible to obtain a phi coefficient which is greater than 1, and that's not satisfactory. So to correct for this, people will prefer to report the V statistic proposed by Kramer in 1946, and it's a pretty simple adjustment to the phi coefficient. If you have a contingency table with R rows and C columns, and you define K equals the minimum RC to be the smaller of your two variables, then you can actually calculate the statistic. It would be chi squared divided by K minus 1 times N, and then you take the square root of that, and then you're done. So this seems to be a fairly popular choice, presumably because it's easy to calculate. It gives answers that are not completely silly. With Kramer's V, you know that the value really does range from 0 to 1. So then let's keep going. And what are the assumptions of the chi-squared tests? So we are on page 17. We're in section 12.5. So all statistical tests make assumptions, as we know, and it's usually a good idea to check that those assumptions are met before you run calculations. For the chi-squared test that we discussed in this chapter, the assumptions are that there would be expected frequencies that are sufficiently large and that the data are independent of one another. So let's go into these a little bit further. We're at the bottom of page 17. So remember how in the previous section we saw that the chi-squared sampling distribution emerges because the binomial distribution is pretty similar to a normal distribution? Well, that is only true when the number of observations is sufficiently large. So what that means in practice is that all of the expected frequencies need to be reasonably big. Moving to page 18. So what does that mean? How big is reasonably big in statistics? So opinions will differ, but the default assumption seems to be that you generally would like to see all of your expected frequencies being larger than 5. Though, for larger tables, you would probably be okay if it was at least 80% of the expected frequencies are above 5 and none of them fall below 1. From what the author has been able to discover, there seems to have been rough guidelines proposed, not hard and fast rules, and they seem to be somewhat conservative. All right, so let's look at the other assumption, that the data are independent of each other. So there's just two assumptions here with the chi-squared test. So one somewhat hidden assumption of the chi-squared test is that you have to genuinely believe that the observations are independent. So here's what the author is saying. Suppose you're interested in proportion of babies born at a particular hospital that are male babies. So if you walk around the maternity ward and you observe 20 girls and only 10 boys, it seems like a convincing difference, right? But later on it turns out that that person only walked into the ward 10 times, and at those times they'd only seen 2 girls and 1 boy. Then that would not be as convincing. So the original 30 observations were massively non-independent, and they were only in fact equivalent to 3 independent observations. So that is a bit extreme and a little bit silly as an example, but it does illustrate the basic issue that non-independence kind of stuffs everything up. Sometimes it's because you might falsely reject the null hypothesis. And as with this hospital example and the ratio of male and female babies, right? It's a silly example, but it does illustrate something. It can go it can go one way or it can go another way. So to give a slightly less stupid example, let's consider what would happen if we'd done the cards experiment slightly differently. So instead of asking 200 people to try to imagine sampling one card at random, suppose that they only asked 50 people to select 4 cards. One possibility would be that everyone selects 1 heart, 1 club, 1 diamond, and 1 spade. All right, and that's in keeping with the representativeness heuristic. Okay, so let's keep going. This is a highly non-random behavior from people, but in this case, we would get an observed frequency of 50 for all 4 suits. So for this example, the fact that the observations are non-independent, right, because the 4 cards that you pick will be related to each other, then this actually leads to the opposite effect, which is falsely retaining the null hypothesis. So if you begin to find yourself in a situation where independence is violated, it may be because it may be possible to use a non-parametric test like a McNamara test or a Cochrane test. Similarly, if your expected cell counts are too small, check out the Fisher exact test. But for now, we're just going to mention that these tests exist. We're not going to go into it in this chapter because describing them is beyond the course of this introductory level book. So let's go ahead and summarize. So in this chapter 12 on categorical data analysis, introductory level, we focused on research studies that involved 1 or 2 categorical variables, We built on what we learned in the previous chapter about hypothesis testing. The key ideas that we went over were about the chi-squared goodness of fit test and the chi-squared test of independence. The chi-squared goodness of fit test, it is used when you have one categorical variable that has 3 or more levels. It is used when you have a table of observed frequencies of different categories, and the null hypothesis gives you a set of known probabilities or counts to compare them to. The chi-squared test of independence is when you have a contingency table, which is a cross tabulation of 2 categorical variables. The null hypothesis is that there is no relationship between or association between the variables, okay? And then we went into effect size. Effect size for a contingency table can be measured in several ways. In this chapter, we noted the phi coefficient and the Kramer's V statistic. Both versions of the Pearson's chi-squared test, they rely on the 2 assumptions, and these assumptions are that the expected frequencies are sufficiently large and that the observations are independent. Various non-parametric tests can be used for certain violations of independence or count assumptions. If you'd like to learn more about categorical data analysis, you could check out the 2007 Agresti book, which is another introduction that is a little more involved on categorical data analysis. If the introductory book isn't enough for you or can't solve the statistical problem you're working on, you could also consider the 2012 Agresti book on categorical analysis. This latter book, the 2012 version, it is more advanced, so it's definitely not a good idea to jump into that right away. And that concludes this chapter 12.